So we're going to talk here about mesh analysis. Now, say we have a problem that we're going to solve where, you know, we have 20 volts and like a, I don't know, a 10 ohm current here and some other ohm, not current, resistor, some kind of 10 ohm resistor and some kind of 5 ohm resistor. Now, traditionally, if we wanted to find the current and the voltage on each of these, what we would do is we would redraw this as a, whatever you call it, equivalent system with a 15 ohm resistor, because they're in series, so we add them together. We'd be like, okay, well, if I assign some random voltage here, if I do a little Kirchhoff's voltage law around here, I get minus 20 plus V equals 0, so V is 20. Or, you know, you could just look at it and say the voltage across the 15 ohm resistor is 20. And we say, okay, well, if the voltage across the 15 ohm resistor is 20, I know that V equals IR, so that means that 20 equals the current times the resistance, so the I is equal to 20 over 15, which is some kind of, you know, number. We can just call it, I don't know, 4/3, okay? Okay, so we have the current going through there. So if I know, now I can kind of work backwards and I can say, well, I know if the current going through there is 1.33 amps, then if I was going to unpack that resistor, then I would have the 2 resistors left. And since it's in series, this still has to be an equivalent system. Since the 1.33 amps goes into the 10, that means the 1.33 amps goes into the 5. So that means that if I want to find the voltage and say, now, this is positive because the current's going into the positive terminal, just because of the way that I labeled it. So I can say the voltage across the first one is IR. In this case, I is, I don't know what it is, 4/3. 4/3? Yeah, 4/3. And the resistance is 10, so I've got 40 over 3, or whatever that turns out to be. Oh, well, yeah, I could have just multiplied by 10. 13.3 volts. And the second one is going to be, again, the current times the resistance, which is 4/3 times 5, which is 20 over 3, which is 6.67 or so. So that would be the voltage across those two elements. And I could check and make sure I'm right. I could do a little KVL by doing a loop around, and I'd say, all right, so the voltage is minus 20 plus 13.3 plus 6.67, and does that turn out to be 0? Yes. All right, so that's not that bad, except it starts to get worse. So if I had a problem instead where I was going to have, say, this guy, and he's in kind of parallel with this guy, who's in kind of parallel with this guy, and whatever. Now all of a sudden, if I want to find the voltage across this guy, I have to basically convert all these to being in series, and these two are in parallel, and then that will be in series with that one, and they're in parallel, so I have to figure out the current here, and then I slowly got to unpack them, figuring out how all of these are ultimately related, which is actually not as fun as it sounds, and it doesn't sound fun at all. So we don't want to do it that way. So I'm going to draw what we have again here, and I'm going to introduce a new topic called mesh analysis. So I had my 5 and I had my 10. How did I do it? Which one was which? 10 and 5. So now, instead of combining the resistors at all, what we're going to do is we're going to say, well, what if I pretend that I know what the current is? Okay, so if I pretend I know what the current is, the current going through that loop, we'll just call it I. Now, since I have I going into this guy right here, that means that there's going to be a voltage drop here of, the voltage drop is, remember, V equals IR. So the voltage drop across that 10 ohm resistor is going to be 10 times I volts. The voltage drop across the 5 ohm resistor is going to be 5 times I volts. So if I'm going to do a little KVL across the side of it, I can say, okay, well, that's minus 20 plus 10I plus 5I equals 0. And so I got 15I equals 20, so I equals 1.33. That's the same answer that I got before. If I want to know the voltage across the 10 ohm resistor, well, I know that that's equal to 10 times I, so that's 10 times the 1.33, which is 13.3. And if I want to know the voltage across the 5 ohm resistor, then I can say that that's 5 times I, or 5 times 1.33, which is that 6.67 that I came up with earlier. So I was able to get the exact same answers without having to know anything about things being in series or in parallel. So that's kind of the fun thing about mesh analysis. Now this is an actually pretty basic example, so let me show you something a little bit more fun. Fun! Fun, fun. We love fun things that are circuity stuff. So let's say that I had this guy, and he looks like this. And oh, that's fine. Let me do this. Alright, so we'll just call him 20 volts for fun, and 3 ohms and 5 ohms and 7 ohms and 8 ohms. No particular reason. Now you can probably see that I have 2 different loops. I have this loop here, and I have this loop here. Now, to be absolutely formal, a mesh is, well, a mesh is a loop. If you look at it, you see the little loop thing. That's a mesh. Don't overthink this, okay? So basically what I can say is that in each mesh, I can say, well, this is one current, and this is going to be a different current. You might say, whoa, 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 though, because what's going on in this little section? It's a great question. So there's a couple of ways to think about it. One way is to say that, okay, if I'm coming down through this guy, along the arrow of this little red person current thing, that the I1 is going with me. So the I1 has gone with me, but the I2 is going against me. So I can say that that little arrow is equal to I1 minus I2. Another way that sometimes it helps for people to see it, I'm just going to zoom in on that little section, is they say, okay, well this I1 is actually coming into here, right? So I can say that the I1 is coming in here. The I2 is essentially coming out up here. And you recognize again that something that's going on here is a linear combination of them. But if I want to know what's going on here, so I can do KCL, which would give me that my ins equals my outs, sum of the in equals sum of the out. So who's coming in is I1, who's going out is that guy and I2. So that means that this guy here is I1 minus I2. So whichever way makes more sense to you, go with that way. Just don't freak out. Just for some people, it makes more sense to think it's current's going with me minus one's going against me. For others, they look at KCL and they go, oh, well, that makes much more sense. So whichever way works for you is great. But eventually, at any rate, we're going to have the same thing we had before, which is the voltage drop across the 3 ohm resistor would say be 3 times I1. 3 times I1. The voltage drop for this resistor would be 5 times I2. The voltage drop for this guy is 7 times I2. And if I'm coming in from the top, I'll put my plus sign there because that's where the current's coming in at. And then I get 8 times I1 minus I2 because that's the current going through there. So now if I'm going to do a loop, I actually have to look at 2 different loops. I can look at loop 1. I'm going to call that loop 1. So the first thing I'm going to do, I'm just starting with the battery, just the voltage source, just because it's easier. Helps me know where I started. So I have minus 20 plus 3I1 plus 8 times I1 minus I2 equals 0. So that gives me 11I1 minus 8I2 equals 20. Now, I'm going to tell you on these problems where you're most likely to make a mistake is just not doing the math right, like adding 8 and 3 and getting 14. That's where I usually make the biggest mistakes, is the simplification and not the actual doing of the circuit part. Get a little bit smaller so you can see. Alright, so for loop 2, I don't know, we'll start here. So we'll start there and we'll go around again clockwise. I have 5I2 plus 7I2. Now, I'm going to say minus 8 times I1 minus I2 equals 0. So that's one way to look at it. You can either say, so I'm going in from the negative side of the resistor, so it's minus the 8I minus I2. For some people, it makes more sense to just say, here's plus 8 times I2 minus I1, because they come in here and they say, well, if I'm coming up through this resistor, if I'm coming up through this resistor, in this case, the current I2 is going with me, and the current I2 is going with me, and the current I1 is going against me. So that's how we get the I2 minus I1. But you can see that algebraically, those are both the same answer. And then I'm going to go through and I'm going to simplify it, so we'll get minus 8I1. This is where math is good. 7 and 5 is 12, and then plus 8 is 20, I think. Yes. Yes. Okay, why am I doubting myself? I don't know, because that's what we do. That's what we do. So divided by 4 gives me 2. Divided by 4 gives me 5. Alright, so now I have two equations, two unknowns. If I want, I can, actually solve them like a grown-up, or I can wimp out and I can put them in my calculator and do a RREF, the reverse reduce, whatever it is, row echelon form thingy. So I've got my little 89 here, and she's gonna help me solve this. She's a good girl. So 11, negative 8 and 20, and negative 2, and 5, and 0. And I'm gonna ref it. And I get some answers. 2.56 and 1.03. And this is an identity on the left, so I know it's good. 2.56. And I2 is some other number. 1.03. Now, what's amazing about this is now I have these answers that can apply to anything on my problem, so whatever I'm looking at. So if I'm coming over here, stick that right there. Alright, so if I asked what the voltage drop was across the 7 ohm resistor, then I would say, okay, well the voltage drop across the 7 ohm resistor is V equals IR. I just figure out what current is the one that's going through there, and so that's I2. So it's just 7 times I2, so whatever 7 times 1.03 is. So I would get that answer. If I wanted to find the power, the power is I squared R. So all I would have to do for any resistor is find the current that goes through that particular resistor and go from there. So like if I wanted to know the 8 ohm resistor, I would just need to decide how I have it labeled and then be consistent within that. Now, let me tell you a little sneaky tricky thing is that, let me recopy this. Okay, so if I have this labeled like this, now before what I did is I manually went in there and I labeled the plus and the minuses on all of these. In real life, by in real life I mean, in school, because that's totally real life. I'm not going to go through and actually label all those. All I'm going to do is I'm going to start straight out looking at the loops. So for loop 1, I'm going to start with the negative 20 plus 3I1. So I'm going to go minus 20 plus 3I1. Then I'm going to go on to the plus 8. And for the plus 8, I have the I1 going with me, and I2 is going against me. And that's exactly how I'm going to read it. So as I'm coming through here, you can see I'm going with I1, but I'm going against I2. So that's how I get that. So I've got that loop, and that's the exact same equation we got before. For loop 2, again, it doesn't really matter where I start. I'll just start with 5 because it's easy, but it's 5 times I2 plus 7 times I2, then plus 8. And now I'm looking at who's going with me, who's going against me. So as I'm coming up through here, the I2 is going with me, the I1 is going against me. So I2 is with me, I1 is against me. I just solve the algebra and I take it from there. One last thing that I want to be sure to mention is it doesn't matter what order you draw your arrows in for the direction of the current. So like with this 20 volts that I had before, I had the 10 ohms and the 5 ohms. And before when I did it, I drew my eye this way. If I were to draw my eye this way, I'm actually going to get basically the exact same equation. I'll have plus 20 as I go through here, then plus, that's supposed to be an ohm, plus 5I plus 10I is equal to 0. So I'll have 15I is equal to negative 20, so I is equal to negative 1.33. And you might say, well, that's the same answer because before we got a positive. Well, yeah, but we had the arrow going the other direction. So remember, it's okay to get negative currents. It just means your stupid arrow is drawn the wrong way. So if somebody asked me, what the current was or what the voltage drop across the sky was, it would just depend on how it was labeled. So Well, I probably wouldn't have labeled it that way. If I would have drawn my current arrow this way, I would have labeled this side the positive and that side the negative. I usually like to draw it to where the current's entering from the positive side. So in this case, I'd say the voltage across the 5 ohm resistor is going to be V equals IR. In this case, my I is negative 1.33. My current is 5, so that's negative 6.67, you say. But again, this isn't the same answer we had before. But if you remember what we had before is on the 5 ohms, I had the plus sign here and I had the minus sign here. So again, we see a case where we just had it labeled wrong. So my answer came out to be negative. See here, my plus sign's on the bottom, so I ended up with a negative answer. My negative sign was on the bottom, I ended up with a positive answer. So these are totally mathematically equivalent, and that's what makes this a really, really powerful method.